Hello, my lovelies. It's Miss Lloyd again, here looking at infinite geometric series. So in my last video, we talked about geometric series and arithmetic series and finding the sums of those. So for this one, we're looking at what if, instead of just a finite series where we have maybe 20, 30, 40 terms, what if it was infinite? What if we didn't have a specific number of terms and it just went on forever? So here there are two options when it comes to geometric. If it's arithmetic, it's just going to go on for forever, and so we can't really find the sum, not an exact sum at least, just, an idea of the sum, infinity. For this one, for geometric, if we have something where our R, or our common ratio, is larger than 1 when we do the absolute value, so say it's -7 or +7, either one, it's either going to be infinitely large or infinitely small. So if I'm multiplying everything by the -7, everything's going to start canceling out and it's going to be infinitely small. And if I have something that's positive, either I'm multiplying a bunch of positives and it ends up being really, really, really freaking big, or I'm multiplying positive by a bunch of negatives and it's going to be really, 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 really negative. So either way, it's not something that we can calculate. However, if I have a common ratio that is smaller than 1 when I do the absolute values, so say I'm multiplying by a half or a third or a fourth, something like that, then it's something that I can find the sum of. Because we're cutting something in half and half and half and half and half and half and half, eventually cutting it in half, it's going to be so tiny that it doesn't actually really make a difference. And we're really converging onto one number. So for our first one, before we really start diving into the formula itself, I want to find the sum of just the first term, the sum of the first two terms, the sum of the first three terms, and then same with the first four and the first five terms, and see if we can notice the pattern that's happening and maybe guess or approximate, mathematically approximate, it's not really guessing if we're using numbers, approximate what that sum might be before we plug it into the formula so it makes a little bit more sense. I'm a visual person, so I have to see what's happening in order for it to make sense. So looking at the first one, just the sum of the first term, which would just be the first term. So 1. Next, I'm going to find the sum of the first two terms. So I'm adding the 1 and the 0.2, adding those two together, and I end up with 1.2. Sum of the 3, I'm adding the first 3 together, and I end up with 1.24. Next, I'm doing the first 4 terms, adding those together, and I end up with 1.248. And then lastly, before I really take a look at what's happening, I'm going to do the fifth term. I don't know what the fifth term is, though, so I'm going to figure out what the pattern is and then just continue that pattern. So here, in order to get from 1 to 0.2, pretty easy, I would have to multiply by 0.2. So I know my ratio is 0.2, or just 0.2. I'm lazy, I don't write the 0, sorry. And so my next term, if I'm writing this out, would be 0.0016. And when I add that together, I end up with 1.2496. Looking at these, we can see that we're starting to get closer to what would be 1.25 or 1.25. So I'm going to make my approximation being about 1.25. I feel like if I keep adding things in, that 6 is going to round up and eventually round up the 9 to round up the 4. It's my prediction. I'm also biased though, so there's that. Because this 0.2 is less than 1 when I do absolute values, I can use that S formula where I have the first term, so 1, over 1 minus my ratio, which is 0.2. When I plug this in, guess what I end up with? Surprise, surprise, 1.25. So this is what we're doing. We're calculating out what that sum would be if we kept going and kept going, and we keep adding smaller and smaller and smaller and smaller numbers together, it eventually converges onto one number. Next bit, we're not going to do that every time. It's just kind of a show and tell. This next bit, we're going to find the sum of each geometric series if possible. If the series has no sum, aka it's way too big or way too small, we'll say so. So for this first one, if I can do this, I need to know my ratio first. I want to do that before I try to figure anything else out. And if you can't tell right off the bat what this is multiplying by, we can do, it's called the common ratio for a reason, so we'll make a ratio of the second and the first term, which ends up reducing to 3/4. And then we can try the second. You can either multiply 48 by 3/4, or you can do 36/48. And this ends up reducing to 3/4 as well, and we take the 12 out of both top and bottom. So that means my r is equal to 3/4. 3/4 is smaller than 1 when I do the absolute value, which means all of my numbers are going to keep getting smaller and smaller. I can notice that because we're going from 64 to 36 anyway, so this would tell me that I should be able to find the sum. Now I need my first term. It's going to go on top. And this will be over 1 minus my ratio, which is 3/4. Plugging this in, we would end up with 256 as our sum of this infinite geometric series. Next one. I am going to fast track through because it's very similar to the previous. So go ahead and pause if you like, take a crack at it yourself, and then you can look at my part at the very end to check your answer with mine. So here we end up with 160/3. If you got the decimal, you can get your calculator to go from fraction to decimal form, or you can do 160 divided by 3 in your calculator that I assume a lot of you guys are using, and find that yourself. Proof is in the pudding, if you will. Next bit, this looks complicated because we have a radical in there. So my thought, in order to get from 6 to -6√3, first off we had to multiply by a negative. Also because the only other thing that's changed is there is now a √3, means we had to have multiplied by a √3. If I multiply -6√3 with a -√3, first it would change from negative to positive, which that's what happened. If I multiply by a √3, that would turn into just a 3, and 6 times 3 gives me 18. So that is indeed my common ratio. So r is -√3. So I'm looking at the absolute value of this. And if you're not sure, if you don't know, the square root of 3, or at least the negative version, would be about -1.73205, and then it keeps going because it's irrational and it just goes on forever and it doesn't actually make any sense. Nothing's repeating. Anyway, plugging that into the absolute value, it is greater than 1. Because this is greater than 1, that means my numbers are going to keep getting bigger. And as they keep getting bigger, it's just going to get more and more messy, more and more complicated. It's not converging onto one number that we can then find a sum of. So, no sum. At least not one that we want to calculate at this point in time. I'm trying to say 7 words at once. It's really not healthy. Next bit still looks a little complicated. And if we can't tell right off the bat what we are multiplying by, again, you can do the ratio. It's called the common ratio for a reason. So I would reduce this. I can speak sometimes, it just depends on the day. Apparently not today. I would reduce to √3/3. And then if I multiplied 2 √3 by -√3/3, the square root 3's would turn into a 3, which would cancel out with the 3 on the bottom. The negative would turn into a positive, leaving us with just the 2. So this is r. If I do the absolute value here, So plugging that into your calculator, we would end up with negative 0.577, and then a bunch of stuff happens because, again, it's irrational. This is smaller than 1 when we do the absolute values, so we can do the sum here, which means I'm looking at my first term being the 6 that goes on top, over 1 minus my negative square root 3 over 3. And here, I'm going to approximate it. We would end up with a sum about 3.8. And I'm totally fine. My students will ask, oh, miss, do we do decimals or do we try to do the fractions? I'm totally fine with you doing a decimal for this one. It's a bit gross as it is. I'm not going to be too picky at this point in time. And here it looks like we have our last 3. This first one, very similar to ones we've done before, so I am going to fast forward through it, and then you guys can check your answers at the end. Check yourself before you wreck yourself. I'm okay. I think I've been inside for too long. And this one, we end up with a very nice, pretty sum of 2/3. On for the next. Oh goodness, this is an infinite series, which is what we've been looking for. These all had the dot, 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 which told us it was going on forever. This one, it has an infinity at the top of it, so we know it's going on forever. Now looking at this, I want to figure out what my ratio is before I do anything else. Because we have this 10 to the negative n, I'm going to rewrite that a little bit. The negative n means that the 10 is going to go to the denominator, meaning it'd be 10 to the power of n, which is the same as saying 1/10 to the nth power. So because the 1/10 is what has the exponent with the variable, that means the 1/10 is going to be my ratio. Because this is smaller than 1 when I do the absolute value, I know I can figure out the sum. So then, oh, I also need my first term, so I'll figure that out by plugging 1 into the situation. So 4 times 1/10 to the first power, so basically 4 over 10, which is basically 2/5, or 0.4, whatever you want to do. So plugging this in, I'd have 2/5 over 1 minus my 1/10. Solving that out, we end up with 4 over 9. And then we're on to our last problem. Again, we know this is an infinite geometric series. So at the other end of the rainbow. I'm looking at the inside of those parentheses, whatever has the exponent. In this case, it's at 1.1, so my ratio is 1.1. And because that is greater than 1 when I do the absolute values, I can't use that sum formula, so we're going to say no sum. And then we're done. I hope you guys had a wonderful ride through this mathematical process. I've really been inside for too long. If you are one of my students, you can find your homework on the LMS page. If you are not, please feel free to like and subscribe. Comment if you have any questions, and please share this with someone who you feel like might need it. Share the love.